You know that A battery powering your remote control? It seems so simple, right? But inside, it's this tiny little powerhouse, and there's a whole hidden world of physics making it all happen. Today, we're going to peel back the cover and really understand the secret forces and resistances that make it all work. Okay, let's start right here. This diagram looks pretty basic, doesn't it? But honestly, everything we need to know is in this simple sketch. You've got your electrodes, you've got this stuff called an electrolyte, and the terminals. So how do these simple parts actually create a current? And more importantly, why does a battery's voltage always seem to drop the moment you actually use it? Let's peel back the layers and find out.
So before we can even talk about batteries, we have to start with the fundamental unit, the building block of all of them, the cell. This is really the basic engine for our whole electrical journey. Every single cell has three main players. You have two electrodes, a positive one we'll call P, and a negative one we'll call N. These are both just sitting in a special chemical solution called an electrolyte. Now, you can think of this electrolyte as the action zone. It's where all the chemical reactions happen that create this electrical pressure. It pushes charge from the negative electrode through whatever device you're powering and then back to the positive electrode. And that continuous flow, that is the current that powers your world.
Okay, now let's just imagine for a second that we have a perfect cell. No flaws, absolutely ideal. In this perfect world, we can measure its true maximum potential. And that concept has a special name, electromotive force, or just EMF for short. So here's the absolute key takeaway. EMF, which we represent with the Greek letter epsilon, is the voltage of the battery when nothing is connected to it. It's an open circuit. Just think of it as the sticker price voltage, the maximum potential it could ever possibly have. So for example, a brand new AA battery might have an EMF of 1.5 volts. That's its max potential, printed right there on the label before you've even put it to work. And here's a pretty cool piece of science history. The name itself, electromotive force, is actually, it's wrong. It's a misnomer. Early scientists thought there was some kind of physical force pushing the charge around, but they didn't quite get that it was actually a potential difference, which is what we now call voltage. And this is so important to remember. Despite its name, EMF is not a force you'd measure in newtons. Not at all. It's a potential difference, and it's measured in volts. It's the ideal voltage of the cell. Seriously, don't let the name fool you. So if EMF is this perfect, ideal voltage, why does the voltage of a real battery tank the second you plug it in? Well, the answer lies in this kind of hidden flaw that every single real-world battery has. It's called internal resistance. Let's go back to our diagram of the cell. To complete the circuit, that charge has to move through the electrolyte. But this chemical soup, it isn't a perfect superhighway for electricity. It actually resists the flow of charge a little bit. We call this built-in opposition the internal resistance, and we represent it with a lowercase r. It's basically like friction for electricity, and it's why batteries can get a little warm when they're working hard. Okay, so let's trace this journey. Our cell starts with its full potential, its EMF. The moment you connect something, a current, which we call I, starts to flow. Now, remember Ohm's law? V equals IR? Well, that same idea applies inside the battery too. A little bit of voltage gets lost or used up, just pushing the current through that internal resistance. And the amount of voltage lost is just I times R. What's left over for your device is the actual voltage you can measure at the terminals, which we call V. And this all brings us to the single most important equation for this topic. The terminal voltage V, what your device actually gets, is the ideal EMF, epsilon, minus the voltage that gets lost inside the battery, which is I times R. So let's go back to our 1.5 volt battery. Let's say it has an internal resistance of 0.1 ohms, and your gadget is drawing 2 amps of current. The internal voltage drop would be 2 amps times 0.1 ohms, which is 0.2 volts. So the real voltage your device gets is 1.5 minus that 0.2, it's only 1.3 volts. That's a pretty big drop. So let's just put this side by side to make it super clear. In an open circuit, when no current is flowing, I is 0. That makes the whole IR part of the equation 0, and the terminal voltage V is exactly equal to the EMF. But in a real working circuit, current is flowing, so you always lose some voltage to internal resistance, meaning V is always going to be less than the ideal EMF. Okay, so what if one cell just isn't going to cut it? We combine them all the time. And there are two main ways to do this. You can connect them end to end, which we call connecting in series, or you can connect them side by side, which we call in parallel. So let's see how this works. First up, cells in series. This is exactly what you do when you stack batteries in a big flashlight. The whole goal here is to get more voltage.
Now, the rules for connecting in series are just beautifully simple. To find the total EMF, you just add up all the individual EMFs. And guess what? The internal resistances add up too. So that's the trade-off. You get a higher voltage, which is awesome, but you also get a higher total internal resistance, which means you could have an even bigger voltage drop if you're pulling a lot of current. All right, now for the second setup, parallel. With this one, you connect all the positive terminals together and all the negative terminals together. This isn't about getting more voltage. It's all about increasing capacity and sharing the workload. Now, I know these formulas look a little scary, but let's just focus on what happens in the most common situation, which is when you use identical cells. In that case, the result is actually super simple and really powerful. The total EMF stays the same as just one cell, so two 1.5-volt batteries in parallel still just give you 1.5 volts. But, and this is the big advantage, the total internal resistance gets cut in half. This means you can deliver a much bigger current without the voltage sagging so much. It's all about endurance and power delivery, not about higher voltage. Whew, we've covered a lot of ground, so let's pull all of this together into one handy toolkit with all the key formulas we've just talked about. Okay, let's do a quick recap of our toolkit. Want to know the real-world voltage your device is getting? Use V equals epsilon minus IR. Curious about how much current your whole circuit will draw? That's I equals epsilon over R plus R. Need more voltage? Stack your cells in series. Need to be able to deliver more current or want more battery life? Connect them in parallel. This table isn't just a bunch of formulas. It's basically your guide to understanding any circuit that runs on batteries.
So, the next time your phone's battery seems to drain way faster when you're playing a game, you know exactly why. It's that sneaky internal resistance hard at work. And that brings up a really fascinating question, right? How do engineers battle against this tiny, invisible resistance to design better, more powerful, and more efficient batteries for everything from our smartphones to the electric cars that are going to shape our future? Definitely something to think about.